This is the session entitled Storage, the Holy Grail for Sustainable Energy. And my name is Joe DeSimone. And as I began preparing for this session, I began looking back and a little bit of historical context. And I think it was in 1880 that the first incandescent installation was installed. It was actually installed aboard a ship, the SS Columbia. And then in 1882, Thomas Edison installed the first steam-powered electrical distribution system in New York at Pearl Street Station. And so it's interesting context. And obviously a lot of competition took place with George Westinghouse, and then life changed for all of us for the better. As you just think about how much electricity has just transformed our world. It still remains to be a utility of expectation in a lot of other places around the world. Clearly, there's been amazing breakthroughs in a generation of power and electricity. And you think about the efficiency of fossil fuel plants that have taken off and really drove so many different economies, and now all the challenges with fossil fuels and climate change. But obviously, nuclear, solar and wind has just taken off as well, and is beginning to make a big impact around the world for all the right reasons. And what's interesting is when you think about all these installations of power generation, all of them are dealing with the delivery of peak power needs. You know, the electricity needed when consumers need it the most. And it's believed that there's a 20x need between peak power and what's naturally generated or at low times. And I've heard anecdotal things that, you know, if we had efficient ways of storing power, the United States wouldn't have to build a new power plant for another 50 years. Just extraordinary capacity that's just not utilized. And so anyway, the generation of power is all around peak power. And so storage and the transmission of that power turns out to be really, really key to a sustainable future, and hence the focus of our session here today. Obviously, everyone in a room is familiar with power storage for their mobile electronics. Yeah. Hopefully safe electronic storage. But lithium-ion batteries has just really taken off, and again, has changed how we live. And the electrification of vehicles is massively underway, and you know, it's interesting the number of households one can run off a car, and that's kind of ratios you think about. You know, I've heard numbers of maybe 10 or 20 homes on a car at certain times. So it's a lot of power stored in these electric vehicles. And then you think about at the utility scale, whether how one stores power to really address some of the peak demand needs is really, really critical. So we're fortunate today to have two leading experts in this regard. We have Rob Piconi, who's CEO at Energy Vault. He's on my far left here. It's really exciting here. Rob is debuting, and his company's coming out of stealth mode here at this meeting. And that's a lot of fun. And it's sort of a soft launch. And we'll hear more about his company. And for full disclosure, Ben Rosen's an investor in his company. And it's just amazing about Ben. He wanted to make sure I appreciate that, having had NIH funding and other things where we do disclosures on a routine basis. And it tells you a lot about who Ben is. But Rob was a graduate at University of Notre Dame and MBA from Northwestern. He's been in a handful of different companies over his career, a lot in healthcare and the energy space, great names like Danaher, Lucent Technologies, Amoco, and British Petroleum. So really seasoned person. And then next to me is an author, a writer, Akshat Rathi. He's a London-based reporter for Quartz and covers science, energy, and the environment. And to my great satisfaction, he has a PhD in organic chemistry at Oxford University. and also a chemical engineering background at the Institute of Chemical Technology in Mumbai. And 2018 Journalist Year of the Award, Journalist of the Year Award from Drum's Online Media Award, so an accomplished writer, and has written for The Economist, the Royal Society of Chemistry, Nature, and The Guardian. So a great panel, and we thought we'd just go through, and Akshat, you want to give us a start?
Yep. I'm going to take you many more years back from 1882. Yeah. I have slides.
1 minute.
So going back to, if any of you attended the aperitif session, if you think about human development, we would put agriculture as a turning point where we went from hunter-gatherers to an organized society to have the ability to grow food almost when we want. But that almost is a crucial point because the seasons don't always work the way we want them to work. And so agriculture needed to be combined with storage. And once we started and learned how to store food, we also learned and got the ability to store other commodities that power our life. So over the millennia, we've stored grains, then we started storing meat in livestock. We learned about metals and used them to great effect. And eventually we got to fossil fuels. And fossil fuels, if you think about them, they are really stored energy. They are energy only when you burn them. Otherwise, they're just sitting there, stored over millions of years. The challenge in the 21st century is that we can't keep burning fossil fuels and putting greenhouse gases out into the atmosphere. And that challenge needs to be overcome in many ways. Storing energy is one. When you think about storing energy, as we had a guffaw from the audience, batteries come to mind first. And here's a historical anecdote. Batteries came before electricity did. So the first battery was invented in 1799. And it was the only supply of steady electricity that we had initially when Volta invented the battery back in 1799 using two metals and an electrolyte between them. So since then, 200 years, and we are still stuck with something of that sort. That feels a little odd. But of course, these batteries are much more advanced than what we had back then. They don't just power smartphones, but they also power electric cars. In the future, the hope is that they'll power electric planes. And one of the biggest challenges that we have, as Joe alluded to, is how to deal with intermittent solar and wind power. There are zero carbon sources. We have a few others, but these are becoming very cheap and are being deployed at grand scales across the globe. And they bring us to a peculiar stage in how we use electricity. So again, something that Joe spoke about, if you look at the chart on the slide, that's an average day in California. So it might be a hard chart to read on the screen, but it basically, the top line is what electricity consumption on a typical day was in 2012. So you started at about 20 gigawatts at 12 at midnight. While people are sleeping, electricity consumption tends to be fairly stable. And then it increases as people go to office and turn on air conditioning or whatnot. Goes down again at lunchtime, and then peaks back up just before dinner. Everybody's got their TVs on or whatever. That was 2012, right? That's just 6 years ago when California started deploying large amounts of solar, utility scale, but also rooftop solar. And what you see in the middle when the sun comes out is the amount of electricity traveling on the grid, on the electric grid, suddenly starts falling. That's because people are consuming solar right from where it's being produced. It doesn't need to go back onto the grid. And you reach this point where in 2018, what this is called, it's called the duck the duck curve, because it's got this shape of a duck. And the duck curve keeps getting deeper and deeper, or the duck gets fatter and fatter. And this is an average day. On certain days, it so happens that California produces more electricity than it can consume. And in those days, it has something that is very peculiar to 21st century, something called negative priced electricity, where the Californian electric grid is paying people to use the electricity. Because if the electricity is not used, the grid can fail, because grid is like pipes, and if you put too much water in it, it'll burst. So you have this happening in California, but you also have this happening in other places where you have a lot of renewables. So Germany, France, Switzerland, the UK hasn't been shown, but UK also has the same problem. Australia has that problem, and within the US, you have that problem in California, in New England, in Texas. And this problem is only going to grow because we are moving away from fossil fuels, partly because of climate change, but partly because of economics. Wind and solar are getting cheap. And so one way in which we are dealing with this problem is through storage. And the oldest form of electricity storage, apart from batteries, is something called a pumped hydro storage. So this is a facility, you can see there's a dam on a river. So there's a small reservoir along the river where you would have hydroelectricity generated as you normally do. You let the water fall on a generator that turns a turbine, the turbine produces electricity. But when you have excess electricity coming from, say, solar or wind, what you can do is use that water and pump it up to that little circular pond at a higher altitude. And when you want that electricity back, all you do is let that water fall back onto a generator and produce electricity. And that's, we've had this technology running for about 100 years. It is about 97% of all energy stored in the world in electricity form is stored in pumped hydro facilities. But these require certain geographies. So only 10 countries in the world have about 75% of all pumped hydro facilities because they have the rivers, they have the mountains. And that's not good enough for where we need to get. One way to address that problem is to try and develop other technologies that make use of gravity. And I'm going to steal the thunder of my next speaker and tell you about it because I happened to get a sneak peek before all of you did. And I traveled to Switzerland and I was able to see what they've built. And my wonderful team at Quartz created this video, which I'm going to play and then let Rob give you the details.
Applause there.
Okay. That was actually quite good. You left out the part about the nice lunch that we took you to afterwards. It's great to be here again, Rob Piconi, and we are introducing a new company today, our company, and speaking publicly for the first time. So we actually decided to pull this up a few months. There's an energy conference in Pasadena in November where we're going to be participating to talk a little more in detail and actually launch the company. Our company is an Idea Lab company. So how many of you know Bill Gross? I think he's been here before and spoken, many of you. It is a real honor and privilege to work with Bill. I've known him about 12 years now. We have not worked together yet through just a series of timing issues. And Bill speaks about timing. If you've followed some of the things he speaks about, like entrepreneurship, what makes a company successful. Bill, the type of guy that really wants to understand how things work and what's behind and always to improve performance, studied companies that were successful and those that weren't. Idea Lab itself has created 150 companies. I think 45 or so have gone IPO. So he has quite a lot of experience with this and working in entrepreneurship. So he studied his own companies, but also 50 other companies. And Bill, being always a big idea guy, if you know Bill, always thought it was going to be about the idea, that this would be the most important factor to whether a company is successful or a failure. But that wasn't the number one item that led to a company's success. You might think people always comes to mind. Hey, it's the people that make the difference. That also was not number one. And it turns out the number one criteria for a successful company or not was timing. Actually, people came second, and the idea actually came third, I think, to the chagrin of Bill. But very interesting. And I think on this theme of timing of us talking about this here at Kent Presents, which I think is the right forum. This is about ideas, new ideas, and I'm not going to speak to you today about chemistry or the things that my two colleagues to my right are much more educated and skilled in than I am. But we're going to speak about conventional science and the innovation around, I think, utilizing conventional science, conventional technology, but innovating around how it's put together and utilized to solve a very important problem today. And one thing I want to emphasize that this is a problem today that's very near term, and that as we speak, if we don't get storage deployed in a larger way concurrent with renewables, we're going to continue to degrade our atmosphere and continue to utilize fossil fuels. So anyway, a pleasure to be here, and I'm excited to begin to talk to you about our technology.
That's great. Thanks, Rob. So, Akshat, maybe just for context, it might be useful to maybe share with the group some of the other approaches for storing potential energy in this regard.
Yeah, so what Rob is doing is essentially, Rob's company is doing essentially picking blocks of concrete up against gravity, storing it in potential energy form, and then when you let it fall, you can turn motors or generators to produce that electricity back. And you could do it in many forms. You could use other forms of using gravity. So there are two other companies that are working on it. One is called QuidNet Energy, and it uses an existing shale gas well. Shale gas, if you know anything about it, is a sort of a soft rock in which oil is trapped. And so to get shale gas or oil out from it, the rock is broken and then the oil and gas is recovered. But once it's recovered, that well exists. And so QuidNet Energy has found a way to pump water into that well. And if you keep pumping water, the rock is soft enough that it gets compressed like a spring would. And when you want the energy back, you release the pressure and the water comes gushing out. You can use it to turn generators and that'll produce electricity. There's another company in Germany called Gravity Power, which is trying to do something similar, where it's built a metal piston that sits in a large hole underground, and it's floating on water. when it's got energy stored in it, and when you want the energy back, you let it fall, and the water is pushed out, and you can turn a motor and generate electricity back. So it's gravity is a powerful energy, a powerful force that we can use for generating energy.
So when I first saw this, and I got a chance to get a sneak peek myself preparing for this, it was ironic for me because I've got an intro slide to a lot of talks I give, and I talk about, when I talk to a lot of students about, places to work in that would be, good career moves, and obviously energy and energy storage is a big topic, and I grabbed something off the internet that reminded me a lot of this. It was basically, folks building an island in the ocean where they core out the center of the island all the way down to the floor, and they pump water out and then let it flow back in. And so in essence, this looks like that, but a land-based system. And so it was fun for me to see this, and it seems very compelling. I get nervous about some of the other technologies about safety. You hear about fracking issues and just earthquake issues, but this seems to me to be a safe, compelling approach. What are the biggest challenges that you see as you begin rolling this out?
Well, I've thought about storage for some time, and in particular, the last 15 years, developing a lot of infrastructure solutions. So Idealab has developed solar infrastructure primarily, and looking at how to solve the challenges of the cost of renewables, because without subsidies or tax credits or support from the government, it gets very difficult to economically prove these things out and make the investment beyond the moral imperative. But now with the developments and some of the infrastructure side and the low-cost materials, and Edison's a company, another Idealab company that's done a lot of work to bring down the cost to a level where it's actually economically deployable, even without subsidies, solar and wind today, as long as the sun is shining and as long as the wind is blowing. So hence this idea that without storage, when the sun isn't shining, it becomes a problem. Without when the wind's not blowing, you have problems when the demand consumption is up in the evening, for example. So our challenge is we looked at solving this problem where renewables are getting deployed now more widely. So there's a chart here, if you look at it and look at the cost that has been driven down now tremendously, and those are tremendous curves, both for wind and solar, of the cost of infrastructure of renewables. The difficulty now is storage. Storage is a requirement. It's a necessity if you're going to economically deploy renewable now in the absence of the sun shining or wind blowing, for example. So because of this aspect, then I'd say, Joe, one of the challenges we saw in looking at new solutions to solve the storage problem, we know that there's a lot of money going behind battery technology and the development of chemistries and to look at solving problems and getting, I think, batteries both that can last longer and not degrade or have loss over time, as well as to bring the overall cost of the battery down. And when we talk about batteries, and it's not just the cost of the battery cell itself, of course. And I think Tesla, you know about, is deploying a lot of large battery installations across the world. But you also have, in addition to the cell, you have the surround infrastructure to be deployed. And those are things like the inverters, all the power electronics you have to use to manage it. And it drives the cost up very, very high, up in the $400 to $500 a kilowatt hour range. We believe that for storage, and this is just a chart here to show some of the costs that you see today, and a lot of these are some battery technologies you see, and to the point that Akshat's made, and Joe as well, on pumped hydro, you see to the far right, pumped hydro is one of the most economical ways to store energy. The problem with it, of course, is it relies on topography. And you heard Akshat say that over 95% of the storage today is actually hydro. But you can't really go and deploy pumped hydro. You have to have the geography, the topography. And so as we looked at the challenges, Joe, we thought, okay, let's start with thinking about pumped hydro, and what if we were able to replicate all the benefits of the storage capacity of water and the length of the storage, as well as get to a cost point that's even well below not only the existing solutions today, but well below even pumped hydro. and eliminate some of the challenges we've had in the past, the topography issue, trying to understand if we can actually deploy something without having environmental problems, not only an environmental recyclable solution, but something that actually is today utilize a material that today we have to pay to get rid of and put in a landfill, for example. So wouldn't that be interesting to have something that actually could have a negative cost to your solution to solve that cost problem? The other thing we thought about here in looking at this solution is something that we could also deploy in a mobile way and next to existing infrastructure and utilizing existing technology. So this was some of the challenges that we looked to overcome. And as we looked at this, and I want to go back one, I know Ben really likes this one and the initial idea, the evolution of the idea, which I want to share a little bit about. We looked at developing essentially and utilizing water as a storage mechanism, these large troughs. And again, we put the ancient Rome here on some of the arches, but we developed utilizing a PVC material troughs where water would flow down and then, like pumped hydro, essentially be pumped back up. One of the problems with this, while we could achieve very good cost levels here, is the efficiency. So we could get to what's called a round-trip efficiency of the solution of about 70 to 75%, which we believe wasn't going to be enough, I think, to be competitive over time. We believe we needed to have a solution that could at least approximate what battery, one of the big benefits of battery, of course, is it's very efficient at 90%.
Yeah, where the round-trip efficiency is really if you put 1 unit of energy in, how much can you get out? When you're putting that in a battery, it's about 90% because you lose some of it as the battery heats up while charging. In terms of mechanical storage, there are other losses that come through, and water in that sense is actually a pretty bad medium because it has so many losses attached to it.
Right. And it's difficult at times in some locations and geographies to actually find, and it's expensive and it evaporates and all these other nice things. So as we developed the idea off of pumped hydro, and which we're looking at is some of the evolution, we looked at low-cost materials. We looked at different civil structures that could be utilized, again with gravity as a thesis, and evolved to something that we believe is quite transformational, that's deployable today. Today meaning we'll be able to deploy solutions beginning the first half of next year. And something that really achieves cost points that are at least half or below half the current capital cost. But as you look over time, or what's called the levelized cost of storage, is something that's going to be extremely disruptive. The solution that we're developing, and I'll put it up here for the first time publicly, is a crane. Big surprise, a crane. Wow, innovation around a crane. It is not just a crane, it is a 6-arm crane. And again, nothing, let's say, so technically difficult about building a 6-arm crane, but it has never been built before, but nothing that we see technologically wrong with that. The other utilization of material we're doing is with concrete. Concrete, and not just concrete we have to make, but discarded concrete. The blocks themselves are quite innovative in the sense of it's concrete, however, it utilizes discarded concrete or recycled material, which has quite a savings and a benefit for the environment. It's also, from an economic perspective, if you look at over time, I mentioned the levelized cost of storage, we achieve levels today that are about 80% below what we see in the market with other battery type solutions. So it's a solution that in terms of performance gives us the 90% efficiency. It gives us also the longevity over time. So this is a solution that can store theoretically for 30 years to 40 years. We understand that with concrete over time there may be some degradation, chipping, et cetera. So there's obviously a solution we have for replacement blocks. It is quite a large tower. This tower is 120 meters tall. So not for your backyard. This is not a consumer device solution. This is something that will exist out near the infrastructures of renewables that are built. So the large solar fields, wind wind turbines and windmills. And to achieve the numbers we've been able to achieve here, you have to have the height, because fundamentally we're utilizing gravity or kinetic energy, which becomes potential energy as we build the blocks up with our crane, and then as we lower them, we can discharge the electricity. Our 6-arm crane will do up to 35 megawatt hours of total storage, and we'll have also a capacity to discharge between 4 to 5 megawatts of electricity per hour. To the point of having multiple day storage, obviously you can deploy multiple of these units as well, so you don't have to deploy just one. And at these cost levels, it's something that economically can be very attractive, and something that in most locations, obviously industrial, not in the middle of a city, you wouldn't put this, nor near an airport, but you would put it out where you're building out a lot of the energy infrastructure. So the other innovation that's very interesting here is this system is not manned. So it's all automated with software. Software, first of all, that's controls the movement of the trolley, because when you're lifting a block that's 35 metric tons, so just to show you here, this is a block of concrete made by machine that is 35 metric tons. We have to control, obviously, things like inertia, wind, have safety protocols if there are storms for it as well. But it is a system that has very, very low OpEx. It utilizes motors from the standard vendors, let's say you would know, Siemens, ABB, et cetera, that are used for the generation. And essentially with these blocks, we build them up in the tower that then is charged when it's fully built, and then is discharged as it's lowered. So the blocks lower at about 2.8 meters a second, about 10 kilometers an hour. And each one of these blocks, roughly, if you're wondering why 35 tons, it's roughly 1 megawatt of storage in each one of these blocks.
So very cool. And there's nothing like something that ticks off the KISS principle and is implementable now without a needed breakthrough. So with that, why don't we open it up for questions? I'm sure there's a lot of thoughts out there. While we wait for the microphones, one here.
Could they be retrofitted into the elevation shafts of buildings?
Could
they be retrofitted into the elevator shafts in buildings?
It's interesting. They could be. They would be sized, obviously, appropriately for that, and we wouldn't use probably the cylinder blocks. We'd customize the brick design, but that's an interesting concept that some people have looked at. We've read that looked at utilizing existing technologies or structures that are already using gravity and generating electricity. So that's an interesting point. I don't know if any of that's being done today. I don't think so.
So there's one retrofit example. There are some ports that use, so if you go to a port where you have these large cargo blocks that are being used, in raising them, you're putting energy in, and some of the ports have now become more energy efficient in that they recover electricity as it's being lowered. And that's something you could do. That's a sort of a retrofit to your existing system, which is being applied in some ports already.
Question. Wait for the microphone here. Right here. And then next one's over here.
Thanks. One question. You mentioned earlier that it would be desirable to put them close to a wind farm or a solar panel farm, for instance. My question is that one of the big users today are these huge data centers that are being built, which have a voracious appetite for energy. What are the differences in the economics of putting it near a wind farm or a solar farm as opposed to putting it closer to the ultimate destination of the utilization of, for instance, the energy, the data farm?
You're certainly cutting to another, almost a separate topic, but a related one will be efficiency of distribution and power lines, right?
That's right.
Yeah, and transmission is one of the big challenges. But to be clear, two things. One is we don't need to co-locate next to the energy source. Okay, we don't have to co-locate, depending on the level of of transmission that would be available. Secondly, the data infrastructure is a large target for us as a market segment. So Google, that's deployed, for example, 100 gigawatts, I think they're the largest infrastructure in the world, is an example of a potential customer, and a customer segment that's investing in for their data centers to power them and needing storage. So both of those.
I would add that data centers already have batteries, and these are most batteries right now in data centers are lead-acid batteries, and they need to be there because data centers need to operate at 100% electricity, right? They cannot go down. Otherwise, you get your Facebook going down or your Google going down.
Right.
And so, right. And so these batteries tend to do that. But one other, battery innovators are coming up with solutions where they could do both, provide the backup power and provide storage. So if you're able to get 100 meters square feet of 100-meter diameter area where you could build this plant, then great. But if you don't have that space, then you could still have battery solutions coming through.
We're going to still need power for our cryptocurrency, so we got to make sure we're up front here.
So I'm wondering, what is the general cost to build this? And then, because of the low OpEx, and I would assume it's not price prohibitive to build it, could it be a solution for rural areas where you just go in and build it, you have a little bit of solar power and use machinery to build the tower, and then it's able to self-sustain? Or self-sustain in the fact that instead of powering 2,000 houses in Stockholm, it does 800 houses and is able to regenerate the power.
Right, so two questions. First of all, on the price, I won't talk about cost today, but regarding how we're going to go to market, roughly we're going to be in the $200 to $250 per kilowatt hour range, which is, if you look at the chart here, quite a bit lower than existing solutions today. And we will be able to optimize that as well over time. Regarding building these in residential, you're bringing up a point of a business model point as well, which is fascinating with a system like this. We don't have to necessarily sell it to someone. We could go build it next to a provider, next to a utility, in front of the grid, behind the grid, and do it as a service model. So electricity as a service, store electricity from utilizers of, for example, solar that get excess during the day, and then we can meter it and sell it as a business model, as a service. So whether it can sit in typically not necessarily pure residential areas, at least for the size of utility scale of this type of a unit, but it could sit very, very close to a residential area, but out in a larger area, obviously.
What I was getting to is, could you put it in a rural place in Africa and be able to give people power that don't have power?
Sure. The only issue is the transport. Yeah. Sorry. The question was about having it in a rural area in Africa, and have that be utilized to give the population electricity. And the only issue we have with that is the transmission of the existing transmission lines that are in place.
So you'll still need some way to generate power to be able to build this tower up. And so it's just a storage solution. It's not a generation solution.
We don't do renewables themselves. So we need renewable energy to feed it.
Yeah. Albert.
Hi. How many configurations did you look at before you settled on the 6-arm crane with the barrels? Because, I mean, how many different, just curious, how long did it take to get to that model? Because one added question is, I was wondering, why do we have the lower levels, why do they have to be concrete blocks? I mean, they can be just a permanent structure, right? Because they won't have much gravity to take back energy.
Sure, the structure itself, the base is actually thinner and lower, exactly for that reason. And then we made the tower, initially we were thinking 80 meters, but we went up to 120 meters to be able to have more capacity. So we did go through, to answer your question, different iterations. We started with a 2-arm crane that had 10 megawatt hours of storage and was able to discharge 1 megawatt of power, and then optimized around the 6-arm crane based on achieving something that, based on customer feedback, was roughly 20 megawatt hours of storage and the ability to discharge at about 4 megawatts per hour. So this came from... Yeah, we spent, I'd say, about almost 2 months going through different iterations, and what I'll share with you is a very interesting tower called the Octopus, we would name it. It's actually 8 arms, which could be a following iteration. But 6 will be optimal for what we see today, also from an economics perspective and efficiency perspective.
I see
just to give
you're
you-
saving money on
Yeah.
marketing. You're just going to call that the octopus.
This is also in the context of being able to innovate on energy storage. A typical battery company requires anywhere between 5 and 10 years to go from a lab scale battery to something that can be sold as a product, and often between $30 and $70 million or $100 million. What these guys have been able to do, because it's a low tech solution, is spend a few $1 million and do it within 9 months. So it's a good way of using already existing solutions.
Question here.
I would love to have a bit more explanation on how the energy gets into the concrete blocks to start with. It wasn't clear to me how the original storage gets. How does it really happen?
So energy is essentially it's potential energy. There are no electrons going into the concrete block. If you lift something to a height, you're storing energy in it. If you let it fall, say you take a glass, this is plastic, I can't break it, but if I had a glass piece and I let it falls and it breaks down. That's because the glass piece had energy in it, which once it falls down, is used to shatter the glass into pieces. So it's simple gravity that is being used.
Yeah, it's just the excess electricity driving a motor that's then consumed to raise it, and then it's stored, and then it's recapitulated.
Yeah.
So
Each arm of the crane has a number of motors that the renewables come in and allow us to lift up the crane.
Yeah.
Another analogy is like a car that goes up the hill and then will coast down. So
I wanted to first say congratulations on this solution. This makes me a little bit pessimistic about Tesla's billion-dollar battery plant in Reno. Is that, you're shaking your head. But my question to you is, this simple solution, barriers to competition for your company?
Great question, and we get them from investors as well. So where is the innovation? So I think part of the innovation is the utilization of what we're building and the method that we're doing it. The software that, by the way, the crane industry hasn't developed software like this that optimizes the movement of the trolley to keep a block or an object, in this case 35 tons, moving at just a pace that's consistent, and then being able to place it and hook it or unhook it in a perfect way. So we have to take into account wind, inertia, and a lot of other things that are happening in the environment. So that software, I would say, is not something that is easily replicated. And then even the design of the concrete block itself. So I think people may overlook civil engineering or mechanical engineering and around what's going to go into the design. We've done seismic work with Caltech, of course, to look at designing that brick in the case of an earthquake, so the structure won't fall down, as well as looking at all the various wind scenarios. So therein lies some of the innovation.
But we should make sure we got 2 separate categories: utility scale power storage versus mobility. Right, so the need for for cars and trucks. I know Elon's had a bad couple weeks here, but just to defend, batteries are going to play an increasingly important role. This is solving, I think, pretty much a different problem, but that complements each other nicely.
And we should mention Joe also has a battery company. He hasn't said anything about it.
No disclosure, Joe?
But that is also, so batteries have a future, and we do complain about the fact that they run out. We are improving on them.
Yeah. If I can add just one thing on that to be clear too, battery will have a place, of course, like it does today. A lot of questions on timing of when some of these solutions are going to solve problems around the recyclability of the material, which is a big problem. The batteries don't last forever, so you have to get rid of them and replace them. That's why when you look at this chart here around the levelized cost of storage, which these models have not been inserted with a solution like ours yet. And now this is the first time, actually the first chart that's been created with this solution, and you're the first to take a look at it. So, but they will have a place. They will solve I think some of the issues around the degradation of power and also the recyclability over time. But it's going to be time. I think Akshat said you're looking at 7-10 years in development, and then I think beyond that as well to get to scale.
Right here.
This may be a naive question, but it's a lot of tonnage you guys are dropping. Is there a possibility of vibration, and what about sound?
Yeah,
Great question.
Great question. On the vibration or on the sound aspect, it's actually quite quiet. I think when Akshat was on, obviously these are much smaller barrels. There's not a lot of noise that's get made also because of the way the trolley is designed and the wheels. It's not it doesn't make a lot of noise. You'd be surprised, but it's we haven't built the full-scale model yet. So, but from everything we see, that's not going to be an issue. Regarding the weight and the size, there's if you look at what we're going to require for land of this, there's a safety field also around. So we have about 80 square meters in diameter that we're going to need for this field to account for if, in the event there's a drop of a block, that we don't have any damage to life or risk to human life.
So clearly, the regulatory and all the different community approvals are going to be important, right? And that's one element of it, the noise. And there's certainly some great examples, Harvard Business School case studies about wind farms off of certain coastlines that you thought would be approved, but were not. So what is some early thinking about that?
Well, a lot of the cases in wind, for example, are related also to agriculture or capability or alternate use of the land. So in Italy, in Puglia, they're delaying the building of a big solar renewable site on the coast there because of alternate use. So for us, because of the scale of these things, typically they're going to be built out where there's large solar fields or large wind fields. So typically we wouldn't have a problem for those areas, but definitely near urban areas, we don't expect these towers to be going up.
Yeah, there was a question up front here. It's coming.
I can probably speak loud enough, maybe not. Can you say anything about what's ahead in the battery area, particularly flow batteries? I mean, look over the horizon just a little bit for us.
So batteries, there's a lot happening. I'm actually working on a series about energy storage this year, and I went in thinking the bigger challenge is utility scale, and batteries are not going to solve it. And I've slightly changed my mind that batteries will play a big part in it as well. That's because the costs are coming down, but flow batteries, and there are chemistries that previously were considered not viable are becoming viable. And so there is a step change coming. You don't know with batteries whether it's 5 years or 10 years, but there's definitely improvement. And so flow batteries are these devices where instead of storing them in packed, tight, solid form, you have large barrels of liquid which have energy, and you pass them through using pumps in a central channel where they produce energy or store energy as you want them to. And they've been around for a very long time, but none of them have become commercial success yet.
And there are other chemical fuel approaches. Australia wants to dominate the ammonia economy and believe that ammonia generation can be a really cost-effective way for chemical fuels. And so there's lots of really innovative things happening out there.
And
right
hydrogen is another one where you split water into oxygen and hydrogen, and you store energy in the form of hydrogen. And also, while we are here, storage isn't the only solution. It is one of the key parts, but other examples of where you could manage this consumption versus generation problem is through transmission. So China is building something called ultra-high voltage DC cables. These are able to transport electricity over 1,000 miles with a loss of 5 or 7%, which is what you are able to do with our cables over 100 kilometers. So you're getting improvements in the ability to transmit electricity. And the other one is down to customers, where there is something called demand response, where you will have devices in your homes which will turn on and turn off based on when electricity is cheap and easily available. And that will be able to help us peak shift. So instead of having your air conditioners turn on when you get home, it'll turn on at 4 p.m., cool the house down for you. By the time you come home, it's not turned on, it's not consuming electricity at peak power.
Yeah, last question in the back.
What's the cost of one of those towers? Or did I miss something?
Our cost that we're...
Cost of the tower.
The 120-meter tower is going to be roughly in the area of about $3 to $3.5 million, all in.
So modest. So we have to end here. I think what's quite clear, we as a society are dealing with climate change issues front and center here, and we are going to have to get our arms around a lot of key things, and storage is going to be one of those really important topics, and that you're going to see increasingly common. And we're going to have to be accepting of certain things if we're going to be dealing with the issues that are front and center here. So I really appreciate and congratulate the entrepreneur here. Thank you. Thank you all.